indefinite integral, we're going to introduce a term called an antiderivative. An antiderivative of a function little f is a function capital F, such that the derivative of capital F is little f. We're going to glance at a few examples. We have an antiderivative capital F equals x to the fifth. Its derivative is little f, 5x to the fourth. We have an antiderivative capital F, which is 4x cubed plus 3. What would little f look like? Its derivative. Little f is 12x squared. Now, you have seen this concept of taking a derivative before. We will introduce the process of finding an antiderivative, which means we will reverse the process. So we'll introduce a term called an indefinite integral. And an indefinite integral of f of x with respect to x is the set of all antiderivatives of little f, and it's denoted integral f of x dx. We'll come back to the notation in a few moments. But first, we want to point out that the graphs of the family of functions that represent the antiderivatives of little f is 12x squared will be shown below. Let's first look at a couple of their functions. One antiderivative is 4x cubed, because if you differentiate 4x cubed, you get 12x squared. But notice that is not the antiderivative we glanced at a moment ago. Well, here it is. It's f2 of x. But there are other antiderivatives. f3 is 4x cubed plus 6, and f4 is 4x cubed minus 3. And what is needed to be noticed is that the derivative of all four functions is 12x squared. So this means that all four functions are antiderivatives of little f. Examining a quick graph showing all four functions plotted, we have in red 4x cubed, and we shift it up 3 units, we get the graph in blue. Shift it up 6 units, we get the graph in green. Shift it down 3 units, get the graph in purple. And this means we can add a constant that would represent any real number to 4x cubed to create the family of antiderivatives. So let's look at notation. We write the integral of f of x dx is equal to its antiderivative, f of x plus c. And the example that we have looked at is the antiderivative of 12x squared dx is 4x cubed plus c. And again, to remind you, when you differentiate 4x cubed plus c, you end up with this function. Now, I want to firm up the vocabulary because the word this function is a little vague. Integrating refers to a procedure of evaluating an integral. And the terminology we use when integrating, well, let's look at these symbols again. We have an integral sign, which you see as this stretched summation is where it actually came from. We have a function that is placed in what is called the integrand. We have a variable of integration, which we antidifferentiate with respect to. And f of x plus c is the antiderivative. C is the constant. Now, to actually perform the process of integrating, we'll first begin with the power rule. The antiderivative of x to the n dx is 1 over n plus 1 times x raised to the n plus 1 plus c, and provided n is not equal to negative 1. Let's evaluate an integral. We'll take a look at, in the integrand, 2x to the fourth minus 8x cubed. allow us to integrate, find the antiderivative. So we take 2, and for the term x to the 4th, n is 4. So in the denominator we have n plus 1, or 4 plus 1, x raised to the n plus 1, or 4 plus 1, minus 8 times, and we look at the term x cubed, where n is 3. So therefore the denominator of the antiderivative for that term is 3 plus 1, x to the 3 plus 1, plus c. Simplifying, 4 plus 1 is 5. We have 2x to the 5th plus 5, minus, and here we need to do 2 computations. 3 plus 1 is 4, and 8 divided by 4 is 2. So minus 2x to the 4th plus c. Let's look at a second example. We have the integral x to the 1.6 plus 2 times x to the negative 5.2 plus 5 dx. Notice the only difference between this problem and the preceding one is that we do not have exponents that are all natural numbers. But the process is the same. In the first term, n is 1.6, so we take x to the n plus 1, or 1.6 plus 1, divide by n plus 1, or 1.6 plus 1, plus 2 times x to the, and again, we observe n is negative 5.2. So x is raised to the n plus 1, or negative 5 plus 2 plus 1, divided by n plus 1, or negative 5.2 plus 1, and then plus 5x. The x is the result of thinking of 5 as 5 times x to the 0. And if we look at 5 times x to the 0, we can then say n is 0, n plus 1 is 1. Hence we get x. Now we just have to simplify this antiderivative. So 1.6 plus 1 is 2.6. So we have x to the 2.6 over 2.6 plus, correct here, plus x to the, and negative 5.2 plus 1 is negative 4.2. And then we'll do a second calculation because we have 2 divided by negative 4.2, and that gives you negative 2.1, plus 5x plus c. Let's look at a third example, one where we have a fractional exponent that we can create from this cube root. So we have the integral of the cube root of x to the 4th, and our goal is to find out what n is so we can apply the power rule. So we rewrite the integrand as x to the 4/3 dx. The denominator represents the root, and the numerator represents the power on x. And then we apply the power rule. X to the n plus 1 over n plus 1. 4/3 plus 1 is 7/3. So we have x to the 7/3 over 7/3. And what you see is the result of inverting and multiplying. So we end up with 3x to the 7/3 over 7 plus c. For any problem that we integrate, we can always check. The check is to simply differentiate. So when we glance at our last example, we will differentiate our antiderivative. This should bring us back to our original function in the integrand. So we differentiate it with respect to x, 3x to the 7/3 over 7 plus c. We bring the 7/3 out front. We go to the 1 less power. The derivative of a constant is 0. And then we cancel the 3's and the 7's. And we're left with x to the 7/3 minus 1, which is x to the 4/3. The bottom number is the root. The top number is the power. And so we end up with our integrand, the cube root of x to the 4th. Examining a few special cases where the power rule would not apply would mean taking a look at the antiderivative of exponential functions, we'll start with e to the x. Since the derivative of e to the x is e to the x, we are reversing the process. Since we're reversing the process, the antiderivative of e to the x is e to the x plus c. The antiderivative of a to the x with respect to x is a to the x over the natural log of a plus c. And remember, the base has to be greater than 0, not 1. Antiderivative of 1 over x with respect to x is the natural log of the absolute value of x plus c. Recall, the derivative of the natural log of x is 1 over x. Again, we are reversing the process. So it's natural to look at a few examples using these special cases. Let us evaluate the integral. In the integrand, you see 2e to the x plus 3 to the x minus e. So we will go ahead and examine each term separately. The antiderivative of 2e to the x is 2 times the antiderivative of e to the x, which is e to the x. The antiderivative of 3 to the x is 3 to the x over the natural log of the base, which is 3. So we end up with 3 to the x divided by the natural log of 3. Lastly, we are looking at subtracting e, not e to the x, but e, which is a number, roughly 2.71828. And so the antiderivative of the number e would be e times x, and then plus a constant. Let's look at a second example. We're going to look at the integrand, and we see 10 over x plus 12 over x cubed. To take the antiderivative, we notice that we have 10 times 1 over x, and the antiderivative of 1 over x is the natural log of x. So we have 10 times the natural log of the absolute value of x. For the second term, plus 12 over x cubed, we can think of this as 12 times x to the negative 3. So if I just, off to the side, write 12 times x to the negative 3, I notice that n is negative 3. We have our antiderivative as 12x to the n plus 1, negative 3 plus 1, over n plus 1, negative 3 plus 1. All that's left is to simplify. 10 times the natural log of the absolute value of x, and then that's followed by the result of 12 divided by negative 2, that's minus 6, x to the negative 2, plus a constant. Well, to conclude, let us look at a word problem. To create a word problem, we give you a derivative. We provide you with a marginal cost. So the marginal cost of producing the xth unit is given by 50 plus 3x plus 2 over x. So this is, in terms of derivatives, c prime of x. The total cost for producing one suit, which I suppose is what this business produces, is $70. Our goal is to find the cost function. We have to anti-differentiate the marginal cost function. The cost function, therefore, is represented by that statement, which we write as c of x is equal to the integral of, and the function in the integrand is the function of the marginal cost, 50 plus 3x plus 2 over x. And we anti-differentiate with respect to x. So we write down our integral. We apply the power rule to the first term. Antiderivative of 50 is 50x. Apply the power rule to the second term. Antiderivative of 3x is 3 times 1/2 x squared. And for the last term, it's one of our special cases. We have 2 times 1 over x its antiderivative would be 2 times the natural log of x. So our cost function is 50x plus 3 halves x squared plus 2 natural log of the absolute value of x plus c. Now this plus c means we have just done what? We've created a family of functions that could be interpreted as the cost function. To find the specific cost function for this problem, we have to nail down what c is. We will do that by taking a look at the total cost of one suit. The total cost of one suit is given. That's $70. So our interpretation is that we'll evaluate the cost function at 1 and solve for the constant c, not to be confused with c of x, the cost function. All right, so we evaluate the cost function at 1. We replace x with 1. And we have 50 plus 3 halves plus 2 times the natural log of 1. Natural log of 1, just make a note off to the side, is 0. So we end up with 50 plus 1.5. So now we have our cost of one suit is 70, and that's equal to 51.5 plus c. And c would be equal to 18.5. So what is our cost function? 50x plus 3 halves x squared plus 2 times the natural log of the absolute value of x plus 18.5. Thank you.